Hi everyone, I am Fabrizio Poletti, a PhD candidate from the University of Modena and Reggio Emilia, and today I would like to talk to you about my latest work, which is about the development of graphene-based electrodes for biochemical applications. We decided to use electrochemistry as a detection technique because it is fast, it is reliable, it has lower costs with respect to other instrumental techniques, and it has an easy preparative. In recent years, the number of works about wearable biosensing has seen a rapid increase. The state-of-the-art devices include nowadays tattoo, lenses and wristbands which can detect physical and chemical parameters of clinical and industrial interest from biological liquids like sweat, serum and tears or saliva. A great amount of works about biosensing are made using the drop casting technique. This technique is very common on a laboratory scale, but it has several drawbacks. For instance, it is not scalable to industrial size, all the deposition steps should be made by hand, so it is also irreproducible and it could take several steps, several layers of coating, and the coating itself could be detached after the use. To overcome these drawbacks, we, in collaboration with the National Research Council of Italy in Bologna, developed fully graphene-based electrodes. These electrodes are made directly with the active element and they can be employed completely bare, without the necessity for a coating afterwards. In these pictures you can see G-paper electrodes. These electrodes are ready to be employed, they are built directly with the active element, which is graphene, and they are printed on PET, which is a flexible transparent support. These electrodes were first tested for their electrochemical conductivity with a benchmark redox species, which is ferrocene dimethanol. Preliminary tests with ferrocene dimethanol demonstrated that our electrodes possess a great conductivity and they respect the Randall-Sevcik equation, as demonstrated by cyclic voltammetries taken at increasing scan rates. This also demonstrates that there is a diffusive charge transport mechanism from the solution to the electrode. G-paper electrodes were then tested using flow injection analysis. With this analysis, we demonstrate that the baseline is stable even if the measure lasts more than 30 minutes. And also tests by injecting ferrocene dimethanol show that the repeatability of the same solution concentration is very high, the relative standard deviation is very low. Graphene paper electrodes were then tested for an application, the detection of NADH, which is a cofactor of several enzymatic reactions. A comparison with other carbon-based electrodes shows that the latter do not have electrocatalysis towards NADH oxidation, while G-paper electrodes can oxidize NADH at a much lower potential. We also performed flow injection analysis on graphene paper electrodes for NADH detection, and we observed great analytical performance, including a very high sensitivity and a very high repeatability of the response, without the need for a coating directly on the bare electrode. To conclude, we developed fully graphene-based electrochemical platforms which are suited for electrochemical applications, as our tests with ferrocene dimethanol demonstrated. These electrodes can be also employed for the detection of a cofactor of several enzymes with great analytical performance. Thanks for watching.